Hi, AP Statistics students. Welcome to our unit on exploring two-variable data. And this time we're going to be going over Notes 3, Linear Regression. If you're new here, I'm Goldie and I'm here to make AP Stats easy to understand. In this set of notes, we are going to be talking about linear regression and the least squares regression line. We're going to be going over an example of it and then talking about the coefficient of determination. So a couple of different things we're going to cover today. So grab your notes, get settled in, and let's go through the content together. So our least squares regression line, least squares regression, or what we call linear regression, allows you to fit a line to a scatter plot in order to better interpret the relationship between the two quantitative variables that you have. It also allows us to use the line to make predictions about our response variable. So least squares regression is the only type of linear regression model that we cover in AP statistics. If you go to other stat courses or expand your knowledge later on and take more advanced stats courses, you'll learn that there's actually a few different linear regression models, one being like the least absolute deviations model, right? But those types of models, if you see those, we're not covering them in this class. I want you to just focus on least squares regression, linear regression. And it's going to be a great fit for us, no pun intended here, because we call a fitted line a line of best fit. The linear regression line, least squares regression line, or for short, we call it the LSRL. And all of these words that we use in this course are going to describe this concept of least squares regression, okay? So it has this equation. Y hat, we say that right, Y hat equals A plus BX. Y hat is our predicted response variable. X is our explanatory variable. B is the slope, and A is our y-intercept. Okay? So if you remember from your algebra days, y equals mx plus b, it's the same thing. M was our slope, B was our y-intercept. M was the slope because it was the coefficient of x, and B was our constant, and that made it the y-intercept. Same thing here. B right now is the coefficient of x, so it's going to be our slope, and then A is our constant, which makes it the y-intercept. Okay. Now, there's two ways to write this regression line. This is kind of probably the way it's mostly written on the AP exam from what I've seen, the bits and pieces, right? Of course, there's the secret bits and pieces, but the bits and pieces that they release, they usually write it like this. So that's why I'm going to try to stick to this form. You might also see it written kind of in the classic y equals mx plus b way, right? Y hat equals ax plus b, where a is your slope and b would be your y-intercept. Again, it switches a and b, but you have to remember that the coefficient of x is always your slope, and then that constant is always your y-intercept. Okay, so even if a and b get switched around, remember that the coefficient of x is your slope, your constant is your y-intercept. Okay. It may be called a and b. The formula sheet does stick to this form right here. Okay. Your calculator will be able to do both ways. It does switch A and B, so just pay attention to what's called A, what's called B. Okay. The way the line is fitted, the way we create this line, is through a process called the method of least squares, where the main idea is that we take the vertical distance between the data point and the least squares regression line, we square it, add it all up, and then we try to make that as small as possible. Okay, so when we look at off to the left here, you see a little point, 4 points with a line going through there. Now, when we draw a line of best fit, it's not going to go through the points. Okay, it's going to just kind of almost summarize the points in a way. So there's going to be a vertical distance between the point and the line itself. So that's what I'm drawing here. I have the point and then a vertical distance between that point and the line. Now, when the point is above the line, that distance is positive, right? When the point is below the line, I have a negative distance, okay? Now, if you add up just all those vertical distances, you actually get 0. Fun fact, right? Fun fact. You get 0 when you add up all those vertical distances. So the method of least squares actually takes those distances, makes them positive, and then adds them all up. And it makes it positive by squaring it, right? So we had this conversation when we went over standard deviation way back when. If you added up all the distances from the mean and standard deviation, you would get 0. From each data point, if you took each data point minus the mean and added up all of those distances, you would get 0. Okay, that was the property of the mean. Kind of the same thing here. Now in standard deviation, what did we do? We squared the distances. And it's going to be the same thing here. We square those distances. And our goal is to make a line that's going to make those squared distances as small as possible. Okay. Now again, other linear models like the one I mentioned earlier, the LAD, it takes the absolute value and tries to minimize that. There's just different ways of doing it, right? For us, we want to minimize that sum of the squared errors, or SSE. Now I bring up SSE, we don't see it in AP statistics, okay? But if you are in a different statistics course, or you take another similar statistics course to AP Stat, you are going to see that SSE come up in different formulas. It's actually used quite a bit in a lot of the two variable models. Us in AP Stat, again, we don't kind of use it right now because we're just an introduction course into all of this fun statistics stuff. But you might see it come up a little bit later on when you extend your knowledge. So just kind of be aware of that if you see that in formulas. If you were to look up information or look in a textbook, you will see sum of squared errors. That's what that means. Okay? For us, we just care about, hey, we have this line. We're usually going to use technology and some formulas by hand, some easy formulas by hand in order to get this line. We're not going to look at a lot of the minimizing side of the sum squared errors. We just focus on the algebraic side of this. Okay, and a big part of AP Stat is, knowing the math, but also being able to interpret. Okay, interpreting the slope and interpreting the y-intercept is huge, and you are definitely going to run into a multiple choice question that's going to assess you on this. Okay, the slope, remember, gives us the change of y with respect to x. So interpreting the slope usually comes by saying for every 1 unit increase on our x, our y is going to change by the slope. That slope could be a positive change or it could be a negative change. And when we interpret the slope, we want to put the context that goes along with that, including the units and including what the variables are measuring. So interpreting slope is going to be big. Interpreting y-intercept is also biggish, right? I say biggish because you can interpret it, but it's actually only meaningful when x takes values close to 0. If x doesn't take values close to 0, the y-intercept interpretation really doesn't matter, okay? So know that the y-intercept represents the value of y when x is 0. So finding it. Okay, again, we're not going to concern ourselves with minimizing the sum squared errors. We are going to use these formulas. These formulas are going to be given on the AP exam formula sheet, and they are algebraic formulas designed to help us find the LSRL. Okay, so again, using the equation from the formula sheet, they use y hat equals a plus bx. To find the slope, which is going to be b, you take the correlation times the standard deviation of y divided by the standard deviation of x. Okay, so the correlation will either be given in the problem, or you will be asked to find it. You'll be asked to find it using your calculator. Okay, you won't have to find the correlation by hand. It'll either be given or you'll find it with your calculator, and I'll show you how to find it with your calculator here in a moment. Okay, and standard deviation you know how to find. Now your y-intercept is actually going to use a property, or a fun fact, as I like to say, because who likes the word property? But fun fact of the least squares regression line. The least square regression line will always pass through the ordered pair x bar comma y bar. the mean of the x's and the mean of the y's. And we're going to use this property because since the least squares regression line is going to pass through it, we know that if we use a point on the line with the slope, we can find the y-intercept. Right? Do you remember that from algebra? Right? If you use a point on a line and the slope, you can find the y-intercept and then write the equation of the line. Isn't that fun? Okay. So we use this property. So we know we can find the mean of the x's and the means of the y's. And then the idea is we know what the slope is, right? We use this formula to find slope. We plug that in with the two means that we find, and then we can solve this equation for a. Okay? Find the slope, find the y-intercept, and then we can make our equation and use it. Okay. Now, to go through this on your calculator, okay, because if you need to find the correlation on your calculator, or you can also use this, you're going to be able to use these steps to also find the least squares regression line on your calculator too. You want to first enter your data into your calculator. The x values are going to go into L1 and the y values into L2. We've done that before. Then we actually are going to go to 2var stats, okay? 2var stats, number 2. 2var stats stands for two variable statistics. And you're going to use your x list as y1, or your x list is L1, and your y list as L2. And then when you run 2var stats, you're going to get your means and your standard deviations that you're going to use in your formula. Okay. Now to get the correlation, you actually have to run a linear regression on your calculator. And the linear regression we're going to run, there's two of them. Number 8 is where you're going to have the a plus the bx on the TI-84s. Okay, a plus bx. And running that is going to get us our correlation. Okay. So finding r, again, here's a little note. We did a process of lists to find correlation, quote unquote, by hand when we were doing an activity earlier. But that's not going to be something you're expected to do on the AP exam. It's good knowledge. It's good to know how to use lists to get what you want to do, but it's not something you're going to actually have to do to get R. You will not have to find it by hand. You will have to show work for calculating the slope by hand, okay, or calculating the y-intercept by hand if it's part of the free response question. So you are going to want to know how to use these formulas, but you don't have to find correlation by hand, okay? So we'll find R by using linreg. I'll go through the steps with an example in a moment. We're going to find R. Once we have those 5 values, your means, your standard deviations, and the R value, then you can find the slope, then you can find the y-intercept, and then you can make your equation by putting them together. Okay? So let's do an example of all of that, all of those steps, right? So in this example, I have a teacher's evaluation score and the score a student got in class. So the x variable represents the the student grade, and the y variable represents the teacher evaluation done by that student. Sorry. So the x is the student grade the student got in class, and then the y is the evaluation score on a scale of 0 to 100, kind of like grades, but it's just a score that the student gives in response to how they think the class went, right? So like this right here, 40, a student got a 40 in the class. They gave the teacher a 10 out of 100, okay? So this is the result for Mrs. H for 10 students, okay? So create the LSRL by hand and show all work. So we're going to make our least squares regression line here. So first, if I'm doing it by hand, yeah, I could find the mean by hand. I could find the standard deviation by hand, correlation, but no. Use your calculator, okay? When it says find it by hand, it means you're going to use the formulas for it. When I say find it by hand, I still want you to find all those other statistics using your calculator. Please do not find those statistics by hand, okay? So L1 is going to go all the x's, and L2 is going to go all the y's. Again, make sure that they are paired up. That's very important, okay? Next, we're going to find the correlation first. I'm going to go to linreg. I'm going to go to L1 and L2 as my x list, y list, and I'm going to pop up my correlation. My correlation is going to be right here, R. Now, a couple of things. If your correlation doesn't appear, what you have to do is go to your calculator. You got to go to mode, and in the mode menu, you have to go down to stat diagnostic and turn it on. Okay. Whenever you reset your calculator, or if you have a brand new calculator, your stat diagnostic will be automatically turned off. You have to turn it on. Now, you only have to turn it on once and then it's on, unless you reset your calculator, which sometimes students do, right? So stat diagnostic has to be on in order for R to appear. The next thing I want you to note is that this has the equation y equals a plus bx, and this tells me what a and b should be, right? Lin reg, I just threw my pencil. Got my pencil. Lin reg, it came right back, so it's fine. Lin reg, I got too excited, will tell you what your slope and y-intercept is going to be. So I know my y-intercept should be negative 29.3, and my slope should be 1.338. But when we have to find the least squares regression line by hand and show all work, we have to use those formulas given to us on the AP exam formula sheet, okay? You can use this fact to check your work, okay? But I am going to do it by hand. The other thing is the R squared value. R squared is actually going to be our coefficient of determination, which I'm going to talk about right after this example we do here, okay? I just wanted to grab the correlation off of this. So my correlation is 0.904. Next, to get all my means and standard deviations, I'm going to run two var stats on xlist and ylist. And then I'll be able to grab my x bar, my standard deviation of my x, my y bar, and then if I scroll down, I'll also get the standard deviation of my y's. Okay? So I'm going to grab all 4 of those values from my calculator there. Okay? Good. Now that I have those 5 values total, now I can use the formulas off of my formula sheet. Okay? So I'm going to take those 5 values. I'm going to find my slope first. So slope was my r times the standard deviation of y divided by the standard deviation of x to get 1.338, which does match my calculator value. So I'm good. And then I'm going to find my y-intercept. So I take the mean, my y bar equals a, plus my slope times my x bar. I solve the equation for a, and I get negative 29.27, which was my, well, very close to the one I got on the calculator. I forget. Rounding issues sometimes are a little off, but that's fine. Okay, and then I put those together to get my least squares regression line, negative 29.27, and my b. Okay, yeah, oh yeah, it does match, right? Negative 29.27 and my b. So that's what my calculator gave me as well. Okay, so if you have to show your least squares regression line by hand, this is the work you want to show right here. Okay, show this work. Okay, show this work. If it's a multiple choice question and you just need to get a least squares regression line, you can definitely use your calculator for that. Okay. Now, what can we do with the least squares regression line? The big things are going to be predicting values and interpreting the slope and y-intercept. So like number 1, the question says, use your equation to predict what evaluation Mrs. H will get from a student who scored an 81. Okay? So a student who scored an 81, the student's score in class was our x variable. And the evaluation Mrs. H get is going to be the y variable. So we're going to take our equation and we're going to plug 81 in for x. Okay? We do the math and we'll get a y hat value of 79.1. So if we were to interpret that, we would say we would predict that Mrs. H would get an evaluation of 79.1. Okay? So that's one of the big ones. One of the big things we can do with our least squares regression line. The next thing would be interpreting the slope. Okay? Interpreting the slope. So this is our slope value. Okay? And what does this mean? It means for every 1 unit increase in x. So x was the student's score. And the units was the grade in class, or points. So we can go by points percentage. So however you want to say that. So for every 1 point increase in a student's score, Mrs. H's evaluation score is predicted to increase, because it's a positive slope. It's predicted to increase by 1.338 points. Okay? So for every 1 score increase or 1 point increase in a student's grade, Mrs. H's evaluation score will go up 1.338 points. Okay? So you want to make sure you have that interpretation of slope down. Okay? Do you think student grades and evaluation students give their teachers are related? Now, there are ways to mathematically determine yes or no to this question. Okay, we have inference procedures to determine this that we might learn about later, but they definitely exist. Okay, right now I just want you to kind of explain based on what you're seeing. Okay, based on the correlation and maybe the scatter plot, if we were to draw a scatter plot of this, right? The correlation is very high. It's very close to 1. So it does suggest a very strong positive linear relationship between student scores and Mrs. H's evaluation. So right now with these questions, all we really have to support our opinion is correlation. We have more advanced inference methods, again, to help us concretely determine, like, yes, they are related, or no, they are not related. Yeah, and we'll get to those. Okay, before I talk about the coefficient of determination, one last note about the least squares regression line on your calculator. We used number 8 here because that was the form the AP exam generally uses, is it has the y-intercept first plus the slope times x. If you've noticed number 4 too, it has it in the y equals mx plus b form, okay, where a represents the slope and b is the y-intercept. So there's 2 ways. You can use either way, okay? Use either way. Use our last example to see that you get the same values. It just depends on what you call y, what you call a, and what you call b, what you call the y-intercept and what you call the slope, okay? So just pay attention to what form you're using so that you don't mix up the slope and the y-intercept, okay? Okay. So be careful of making predictions beyond what the data shows, okay? Extrapolation is when we use a regression line for a prediction that is outside the interval of the x values that we used in our data, okay? Predictions are not often accurate, okay? So please be careful of extrapolation. The other caution is correlation does not imply causation, okay? And if there was a motto I could repeat throughout this whole course, it'll be that. Correlation does not imply causation, meaning because you have a strong correlation, that does not mean that the explanatory causes the response. Right? It does not. Correlation does not imply causation. There could always be a reason for the correlation. And I have a funny example. Okay, there was a serious study done that actually showed a strong positive linear relationship between ice cream sales and homicides in New York City. The more ice cream that was sold, the higher the number of homicides were in the city for any given day. So the more ice cream that was sold, the higher the homicides were. The less ice cream that was sold, the less homicides they were. There was a very clear, strong, positive linear relationship. So does that mean that correlation implies causation? Ice cream sales cause homicides. So if we stop selling ice cream, we have no more homicides, right? Well, it's a kind of a silly example on purpose, right? Of course, that's not the case. Why does that graph show a strong positive linear relationship? The answer is weather, right? During the summer, statistically during the summer, there's more ice cream sales. There's also more homicides that occur during the summer, okay? And that is the reason, that is the driving force behind this correlation. Okay, so it's a silly example. It's supposed to be silly on purpose to show correlation does not imply causation. So even like something like the evaluations between grades and the teacher evaluations, where something correlation, it feels like correlation implies causation. But there's always something that could be another driving force behind the scenes, and you got to be aware of those. Okay. Okay. Last thing we're going to cover is coefficient of determination. So the strength of a prediction, which uses a least squares regression line, does depend on how close the data points are to the regression line. If you have points that are far from the regression line, your predictions are also not going to be accurate. Okay, so we have a mathematical approach to describing the strength of your predictions. Okay, and that's via the coefficient of determination. Okay, so it gives us a proportion of variation in the values of y that is explained by the least squares regression line, basically telling us how strong how strong of a prediction we have. Okay, how I don't want to say because a lot of students are going to misinterpret this. Okay, the script is the proportion of variation in the values of y explained by the least squares regression of y and x. That's the official AP Stat script that I want you to follow when you are interpreting the coefficient of determination. In layman's terms, it's just a way for us to measure how strong our predictions are. And when I say how strong, I want to say like how accurate our predictions are. But I don't want you to take that too far and say, oh, it's the probability that our predictions are accurate, or it has an 85% chance of being correct. It's nothing like that, okay? So don't take my layman's terms too far, okay? The layman's terms is it's just the strength of a prediction, right? The higher your percentage, the stronger your prediction is going to be, okay? Take that with what you will, okay? It actually, to determine it, it's pretty straightforward. It's actually the correlation coefficient squared. So it's going to be the correlation squared. So in our last example with the teacher evaluations, our correlation was 0.904. So the coefficient of determination is we're going to square that value, okay? Which is why the coefficient of determination symbol is r squared, because it's literally r squared, okay? So we take that, we get 0.818. We also report that as a percentage. You can report the coefficient of determination as a decimal or as a percentage, either or, okay? But whenever we use a regression line for prediction, we also include the coefficient of determination as a measure of how successful it is in making that prediction. Again, don't think of it as in terms of like a probability or anything like that. Just more as a measure, meaning the closer that percentage is to 100, the better the prediction is going to be. Okay. If you were asked to interpret the coefficient of determination, I want you to use this script. 81.8% of the variation in teacher evaluations, which was the response, 81% of the variation in teacher evaluations can be explained by the linear relationship it has with student class average, okay, which is the explanatory variable. Okay, so what's in parentheses you don't have to include in your description there, but I want you to use that script when you are interpreting the coefficient of determination on the AP exam. Okay. And that brings us to the end of Notes 3 today. So if you're still with me, thank you guys so much for following along. Please hit the like button and subscribe to my YouTube channel for more great AP statistics content. And until then, I wish you endless statistical success, and I will see you in the next video.